a little bit. But remember all the stuff about chemical reactions represented by chemical equations and the stoichiometry of a chemical equation. Remember all that stuff because we're coming back to it after we talk about this one type of matter called a solution. Okay, and we're going to talk about solution concentrations. So you find solutions actually right here. So this is kind of the logic tree. You can have matter, all matter is made up of atoms. It has mass and occupied space, okay? Those atoms then can be arranged in an orderly, we use chemical formulas. It's a pure substance. Either it's a pure element or it's a compound. Or that matter can be just kind of two or more pure substances tossed together, and we call them mixtures. So under mixtures, okay, it can be heterogeneous, which means it's chunky, I think, okay, or it can be the same throughout. It's homogeneous. If you have a homogeneous mixture, you have actually something called a solution. Now, granted, what comes to mind when I talk about solutions usually is people think water, a water solution, but it doesn't have to be. It's just a homogeneous mixture. So a solution is just a homogeneous mixture of two or more pure substances that are physically combined. Now remember we talked about this clear back in Unit 1, that the cool thing about a mixture is you should be able to, one way or the other, to separate it back out into its components, and we can. If you're kind of a visual sort of person, we can kind of think of a solution. Let's go with, here's my beaker, and let's go ahead and make it a liquid. Okay, the thing that's in my major amount we call the solvent, and the thing that we add to it we call the solute. And we could have more one solutes added. So if you take the solvent, which is in major amount, plus the solute, or solutes, that adds up to equal the solution. So that's kind of what we have going on there. Now, if the solvent is water, if the thing that's doing the solvent is water, which it doesn't have to be, like this says, then that means that we have what's called an aqueous solution. It just means the solvent is water. You know, if you've done much with like painting or preparing wood to be painted, you know that you go out and a lot of times those strippers, those things that get the old paint off are called solvents, okay? And they're counting on, because of the nature of the paint and the nature of that solvent, stinky turpentine or whatever, that the solvent will dissolve the paint, so. All right. So the most common sort of solution is this, where basically the solvent we have as liquid, and we're adding a solid solute that hopefully will dissolve, make us a solution. Example of that is dissolving salt into water. Okay. This one, anytime you drink a carbonated beverage, you are drinking a solution, basically sugar water, carbonated beverages. It's sugar water, and also what's been added to make it fizzy is carbon dioxide. So carbon dioxide is a solute added to your sugar water. We can have two liquids, in the case of vodka, ethanol and water. Okay. And then this one is kind of interesting too. You can have a homogeneous mixture that's a solid, and we call that a solid solution. A really good example are different stainless steel, different grades of stainless steel. Stainless steel is prepared by taking different metals, melting them all down, making a homogeneous mixture as they're a liquid, and then letting it cool. So when we use stainless steel, basically we are using a solid solution. I think that's kind of cool. But mostly what we're going to talk about now, switch gears and just talk about aqueous solutions. And tomorrow, actually you're going to be doing, I think I mentioned a lab on stoichiometry of sodium bicarbonate reactions. Okay, so when we talk about how much solute is in a solution, okay, there are a couple of different ways I want to talk about how concentrated the solution is in terms of a solute. Usually it's per given amount of solution, but sometimes it's the amount of solute per given amount of solvent. And we're not going to hit that this semester, but I'll kind of throw a term out there in case you stay in chemistry. This one down here, per amount of solute per given amount of solvent, that's actually molarity. So if you run into that term, and the symbol for molarity is a lowercase m. Again, we're not going to talk about that. But I do want to talk about two ways of saying how concentrated a solution is in the amount of solute per given amount of solution. So before we talk about kind of the numbers part of it, just the generic terms, if somebody says you have a concentrated solution, then right away you're conjuring up, oh, it must be a lot of solute in that amount of solution. And you're right. If somebody has a dilute solution, that means it's low on the amount of solute per given amount of solution. So those are just kind of relative terms without the numbers. Okay. So with regard to numbers then, we're going to do a couple of different ways to express how concentrated a solute is for a given solution. We're going to go with grams of solute per liter of solution, G per L, grams of solute per liter of solution, and we're also going to go with moles of solute per liter of solution. And actually in Thursday's lab, we kind of dabbled in that. Okay. So again, if you're kind of a visual person, okay, this first one, these are going to be aqueous solutions, honestly. We're going to say, for instance, if you have 1 liter of solution, my abbreviation for solution is SOL''N, okay? You're going to have, what, X grams of solute. That is grams per liter, grams of solute per liter of solution. Down here, again, if we have 1 liter of solution, SOL''N, we have, I'll put Y, moles of solute. Okay, so that is molarity. So notice that these both deal with volume of solution, and one of the things way back when, and you already kind of know this, is that if you put a can of pop in your freezer, what's going to happen?
It's going to bust.
It's going to bust. Yeah. So the thing about water is that it occupies more volume as a solid and less volume as a liquid. Water's kind of strange like that. But if we were to watch it before it busted, okay, if it was like at, let's use Celsius temperatures. If it was like at 22 Celsius when you put it into your freezer, okay, this is the volume. 22, okay, 20, 18, 7 or 16, 14, 12. It's actually going to get smaller volume as the liquid cools down. We talked about this a little bit. And then about 4 degrees, this is what we call maximum density, 4 degrees Celsius. And then it's getting ready to form a solid, and then it finally kind of fluffs out and bursts your can. So my point here is that liquids occupy different volume at different temperatures. So these actually are what we say temperature dependent. And usually it will say, if you're given a grams per liter or moles per liter, it usually says like 25 degrees Celsius or something like that, or 20 degrees Celsius. Okay, so let's work a problem. This is a sugar solution. Sugar's pretty darn soluble. Not all things are soluble in water. And if we draw a picture of this, which I really, working these a lot of times, whether I need it or not, we'll draw a picture. Okay. So if we draw a picture of this, we have, as prepared by dissolving, 32.3 grams of sucrose, 32.3 grams, I'll just write the word sucrose, even though I have the formula up there, in 25 milliliters of solution, or preparing, 225 milliliters, 225 ml solution. So there's my picture. And we're going to work with the same scenario to get molarity, but this is getting it in terms of grams of solute per liter of solution. So what I'm hoping is that you recognize that this G/L means grams of sucrose per 1 liter or liter of solution. So if you don't make it too complicated, it looks like I'm making it complicated. Basically, you're going to take this grams of sucrose and divide it by the volume. Now, granted, the volume's not liters, but we can fix that. So here we go. Solution, no pun intended, the solution to the solution problem. Okay, how I would work it is just simply slap that mass, which is 32.3 grams of sucrose. You can write sucrose if you want, or go C12H22O11, divided by the volume that was given, 225 mils of volume. So now this won't give us G/L. We need to fix the milliliters. So we can do that if we put the next term as 1,000 milliliters over 1 liter. So 1,000 milliliters of solution over 1 liter of solution. Now units will cancel that we need to cancel, and we're done. Units of milliliters solution both cancel. We're left with units of grams per liter, which is perfect. Round according to 3 sig figs, and the answer is 144. And if you wanted to put 144 G/L, you could. Same thing. 144 grams.
I have a question. So I just, like before I did the problem, I turned the milliliters into liters. Is that okay?
As long as you showed your work, yeah.
Okay.
Yep. Did you like show it the factor label with it? Yep. That's fine. Any questions about that? Now, we're going to take the same solution, and now we're going after how concentrated is it with sucrose in terms of molarity. And if I was going to do my notes again, I probably would do them differently, but I'm just going to do with what you have in front of you, so, or what I have my slides. So we're going to piggyback on this answer. It's the same solution. Now we want it in terms of moles per liter. Okay. So what we have from that one is 144 grams per 1 liter. And we want moles per 1 liter. So what you're faced with is basically a grams to mole conversion. And we know we've done a lot of that recently. To go from grams to moles, we're going to use the molar mass of sucrose. And that's exactly it. So the molar mass of C12H22O11, we take 12 times 12.01 plus 22 times 1.008 plus 11 times 16.00, rounding to two decimals. I got 342.30 grams per mole. So you have to, on your tests, on your Unit 4 exam and your final exam, show that. So we're going to use that as a conversion factor. So remember, and sometimes on my answer key, I won't leave it that, I will kind of do 342.30 grams per 1 mole, just so I know how to use it as a conversion factor. All right. So again, we're going to piggyback on our last concentration, which is 144 grams of sucrose, or C12H22O11, per 1 liter of solution. We want grams to cancel in the numerator, be left with moles, so we need to use what? The flipped version of the molar mass. So if we go ahead and insert the molar mass like this, 1 mole, and I know I went ahead and wrote the formula for sucrose, but you really wouldn't have to be that explicit, I don't think, since there's only 1 solute. So 1 mole over 342.30 grams. Grams will cancel, and we're left with moles of sucrose, or moles of C12H22O11 per liter of solution, which is awesome. Looks like we need to round according to 3 sig figs again, and I got 0.419. And what that explicitly means is 0.419 moles of sucrose per 1 liter of solution. But honestly, I don't know anybody who writes it that way. They just put 0.419 big M, molar. sucrose.
Okay, I have a question. When I put it into mine, it says 0.42068.
Did you took,
Yeah.
okay. Well, it could be that I carried over, the,
So it'd be 0.421.
good. Okay, so what I tell students is the big M, which is great, which is molarity, molar, however you want to affectionately call it. But when you go to work a problem, and I'm going to show you what I mean by this, you don't leave it as the big M. You unpack the big M. Molar means moles per liter. You can't use it as a conversion factor like we're going to be using it here in a minute. So, let's see, I think I got this one. So in this, and this is actually important for making up solutions. So basically, we have these volumetric flask that contains 250 milliliters of solution. It will usually say 250.00 milliliters because it's known, it's really pretty accurate. So I like to kind of pretend that I'm at one of the factories that they're making volumetric flasks, and they are calibrated. So each one, you can imagine, there's one line that comes up the neck. You're like, where does it? Well, it depends. You know, if you're paying a lot for your glassware, they'll make sure it's at the right spot. So I think that's kind of neat. So here's a still image from your textbook doing the same thing, using a funnel to get the solid in there, okay? Using the wash bottle to kind of wash in case they had any solid solute that's kind of sticking on the sides. The other thing that they probably did is take the wash bottle and kind of rinse out looks like a test tube, I don't know. Okay. Notice just a little bit of solution of a solvent down here. Okay. And then mix it well, and then actually kind of top it off with the rest of the solvent, probably water, using a squirt bottle. So let's take a quick look at these. I think I'm going to go ahead and make some of these kind of pare down what I've got going on there. 1459. Where'd you go? There you are. Okay. So for the first one, if you just do, you can do C for extra credit in case you run out of time. So C is extra credit. Let's just go ahead and make it 5 points so you know what you're after here. Not too bad. Be careful of A, that molarity, which is what you're after, is moles per liter of solution. And so you're going to have to, fix the milliliters. So down here then, we take it up a notch. Those give you moles and volume. Down here, it just gives you grams. It doesn't give you moles. So we'll go ahead again and make C worth 5 points extra credit. The thing about C, though, well, I guess I should say my hint is you're going to have to use the molar masses of the CPD stands for compounds. You have to use the molar mass of the compounds in these problems. And for C, you're going to have to fix the mass from milligrams to grams before you do your calculation. Oh, and then you also have an issue for C for that. And then let's go ahead and make 63 for regular credit. It gives you the mass and the volume, and you're supposed to knock out molarity. Okay? So let's go on to the next part. I have to remember that, so that's like 7, how many minutes? Oh, I have a time. I have a little clock up here. I have 10:24. All right. So anytime you have, I think of molarity as like another property, a physical property of the solution. So, for instance, if somebody gives you the grams per liter, grams of solute per liter of solution, you can actually use it as a conversion factor to go back and forth between grams of solute and liter of solution. If somebody gives you molarity, that property of the solution, of course molarity unpacked is moles, I'll put it up here, molarity unpacked is moles of solute per liter of solution. So again, molarity, you can go back and forth between moles of solute and volume of solution. And I'll go ahead and throw this in at you, although we won't talk about it today. Remember we talked about, remember the egg? Okay, so eggs, we said that it's a weight percent shell, weight percent white, weight percent yellow, okay? You can actually do that with solutions, and a lot of times solutions, like under your cupboard, cleaning solutions will say weight percent of a component. So you can use weight percents to get back and forth between mass of, here I'll do it this way, weight percents are grams of solute per 100 grams of solution. So you can go back and forth between grams of solute and grams of solution. Okay, so let's just go ahead and work a problem. So someone went ahead and prepared a salt solution, and they prepared it and they told you what its concentration was in terms of grams of salt per liter of solution. So actually the next slide I go ahead and unpack that. I should never see you work a problem where you just leave it G/L or big M. Okay, that's not going to cancel right. So in this case, and you're going to see, I think 2 slides from now, I'm going to show you that the first term when we work this problem is we want to know what volume of solution to measure out to get a target 22.3 grams of sodium chloride. So here's how this works. Again, keep in mind that when they gave you the concentration of sodium chloride in the solution, 14.3, that meant 14.3 grams of NaCl per 1 liter of solution. And we can kind of do some things with this physical property of the solution. We can flip it, 1 liter of solution over 14.3 grams, or we can even flatten it out. It's the same thing for this solution. So thinking of it as it is, or the reciprocal, the flipped version, or flattened out, that's hopefully getting you thinking how you can use it, in this case, to get from grams of NaCl to liters of solution. All right, here we go. So we can go from grams of NaCl to liters of solution using that property of the solution. 1 liter of solution is equal to 14.3 grams of NaCl. Like, for instance, if I wanted 28.6 grams of NaCl, you guys would tell me I need 2 liters of solution, right? Okay, but let's work the problem. So the first term is going to be our target mass, our 22.3 grams of NaCl over 1. And then I want grams of NaCl to cancel. I want to be left with liters of solution, so I'm going to use it like this. Put 1 liter of solution over 14.3 grams NaCl. My grams of NaCl have canceled. I'm left with liters of solution. I'm done. So it looks like rounded to 3 sig figs, you get 1.56 liters of solution. That's it, man. Okay. So let's work another one. Okay. Now sometimes it's hard to know how explicit you need to be in your labeling. Like a little bit ago, I get tired of writing the formula for sucrose, so I would just write, I might even not even write it at all, because there's only 1 solute, you know. But if you have more than 1 grams, so for instance, those stoichiometric calculations we've been doing, we have grams of 2 different things. So in those, you had to be explicit. So, okay, let's work another one. In this case, somebody prepared the solution for you. It's potassium dichromate, and they prepared it 0.255 molar. And the question here is, so actually we're going to use that as conversion factor. Our first term is going to be that 0.015 moles of K2Cr2O7, and we are going to get to milliliters of solution. So this slide is just to kind of have you start to think about the molarity, kind of the physical property of the solution. How can we use that as conversion factor? Well, 0.255 molar means 0.255 moles of K2Cr2O7 per 1 liter solution. We could also use the flipped version if we need to. 1 liter solution per or over 0.255 moles of K2Cr2O7. Or we could use the flattened out version, which for this solution, 1 liter solution is equal to 0.255 moles of K2Cr2O7. So here we go. We can go from moles, which we were given, our target moles, to liters of solution using the molarity. But don't be caught off guard by this. Notice it wants volume, not in liters, but in milliliters. So we can go from liters of solution to milliliters of solution using 1,000 milliliters solution is equal to 1 liter of solution. So we're going to have like, what, 3 terms this time. So the first term is going to be your moles of 0.015 moles K2Cr2O7 over 1. And then we want moles to cancel, be left with liters. So the next term is going to be 1 liter of solution over 0.255 moles K2Cr2O7. And then we need to get the liters to cancel, be left with milliliters. So we put 1,000 milliliters solution over 1 liter solution. So if we go back and allow things to cancel, notice moles have canceled, liters have liters have canceled, and we're left with units of milliliters, which is perfect. So I'm liking only 2 sig figs for this. So the answer would be 59 milliliters of solution. Okay. All right, seems like I got maybe 2 more. Okay, let's do another one. This is a little bit different. This is actually, we're after moles given volume. But you see the big M there? Think of that as, that's not going to be our first term. Okay, and we're going to need to unpack that. So I don't think I have slides doing so, but I would take that and I would say that's 0.108 moles of CaCl2 per...
That's the next one.
Oh, it is? 1 liter solution. It does
Well,
unpack
not
it?
unpacking it, but the...
Yeah. The solution.
Yeah.
Thank you. So I would unpack that usually in the margins. So here we go. Yeah. So we're going from milliliters to moles. So molarity is in terms of moles per liter. So first we have to fix our milliliters. That's how I think of it. Of course, we can fix our milliliters by recognizing 1,000 milliliters is equal to 1 liter. And then we can go from liters to moles using the molarity. That's it. So specific to this problem, the first term is going to be the volume in milliliters. So 75.0 milliliters of solution over 1. And then we're going to fix it to liters, so then we'll put 1 liter solution over 1,000 milliliters of solution. So our milliliters of solution have canceled. And now we're left with liters of solution. Now we're going to introduce molarity. So now this is going to be what? The non-flipped version of molarity. So if we just go ahead and insert 0.108 moles of CaCl2 per 1 liter of solution, liters of solution will cancel. We're left with moles of CaCl2. I'm liking 3 sig figs. So 0.00810 moles calcium chloride. That's it. Okay. Is there one more? Is this the last one? Sign a slide? Okay. Good. Okay. Okay, this one's a little bit different, isn't it? So it says, what mass of glucose is in 125 milliliters of 0.432 molar C6H12O6 glucose? So again, what I would probably do in the margin somewhere is unpack that. So what that big M means is 0.432 moles C6H12O6 per 1 liter of solution. So I diagram this one. It's a little bit different because I think I diagram it, but it says what mass, so actually I'm after grams of sucrose is in 125 milliliters of solution. So actually when I work the problem, it's going to kind of go like that. So we're going to start with the volume. And we're going to use molarity to go from volume to moles, but since volume is in milliliters, first we have to get it into liters. So that's the first step. We can get to liters by recognizing 1,000 milliliters is equal to 1 liter. And then once we have liters, then we can use molarity to get to moles. So the next term is to use molarity to get from liters to moles. But we want mass, so then we're going to have to use what we talked about earlier in the class. To get from moles to grams, we have to use the molar mass, periodic table, and the molar mass of glucose. Whew! And that's it. So the way this works then, or looks, is we put the volume over 1, so 125 milliliters solution over 1. We convert it to liters by introducing a term, 1 liter solution over 1,000 milliliters of solution. And then we introduce molarity, and we're going to use what? The unflipped version of molarity to go from liters to moles, 0.432 moles of glucose per 1 liter of solution. And then we need to have calculated the molar mass, which we did a few slides ago for this same compound, I think. So we need to use the molar mass, which is 180.16 grams of glucose per 1 mole of glucose. So if we look at things that have canceled, that's one of my favorite points of working a problem like this. So milliliters have canceled. Liters have canceled, and I got moles have canceled too. We're left with grams of glucose, which is perfect. 3 sig figs, you should get 9.73 grams of glucose. And that's it. Do you see where actually in doing this problem, you have actually come up with a recipe? You can dissolve 9.73 grams of the compound in 125 milliliters of solution, and your molarity is going to be 0.432 molar. So you never know when that could come in handy. All right, so let's take a look at these. Now I went ahead and crossed off 65 and 67. So those are out. And these are not multiple problem ones, so we'll take a look at these. I think we'll go ahead and just diagram together how these could be worked. I say could be worked instead of should be worked because a lot of times with this sort of chemistry problem, there's more than one way to work it. So I'm looking for 1371 right here. Okay, so looking at the first one. Okay, so 71 says calculate the mass. And see, if you want to kind of read through it straightforward, I would go calculate the mass. So over here, I would put on the right, I would put question mark grams. Calculate the mass in 35 milliliters of, and so actually that's going to be my first term, 35 milliliters. And then it gives me molarity. So let's see what we can do with that. So of course, what we've been doing is a pattern. We can go from milliliters to liters using, you know, the metric system. And then we can go from liters to moles using the molarity. And then how are we going to go from moles to grams? Molar mass, mm. That's it. Perfect. 72. Oops, didn't have to do 72. 73, and the answers to all these are in the back of the book. So, in this one, I'll just still kind of read left to right, maybe. Or I think I'll read the whole thing. It says, a chemist wants to make a certain volume of a certain molarity KCl solution. How much KCl in grams? So, it looks like we have another question mark, grams. Should he or she use? So, it's funny, like, if you're playing euchre, which I don't know if anybody plays euchre, but they say never let a trick go by, you know, so like if you can take the trick, go ahead and take it, even if it means doing something odd to your partner. And this is kind of like you never start with molarity. You never let trick go by, and you never start with the molarity term. I never would anyway. So the other thing we have left to start with here is our volume. So this one's going to go 2.5 liters of solution. And we can go from liters of solution to moles using molarity. And you told me we can go from moles to grams using molar mass. So that's perfect. And last but not least, how many liters? So I'm going to put question mark liters of a given molarity. I'm not going to start with that one. Contains 1.5 kilograms of sucrose. So in this case, 1.5 kilograms is going to start out. But notice I'm going to go to grams using the metric system. And then I'm going to go from grams to moles using the molar mass. And then I'm going to go from moles to liters using molarity. So that's kind of how that works. Any questions? So those will both be due on Friday. Awesome. I got 10:42. So that's it for today.